find the graph paper. There it is. I usually like to have that open first, but since I had Screencast-O-Matic out there, rather than minimizing it, opening this, and going back to that, I thought I'd just, good. Ashley's here. Okay, double their class size. Top part of the alphabet coming in strong. The rest of them, not so. Okay. And I don't know if you didn't see it because I don't have a projector on yet, but it just, I have this file up here that has graph paper and white paper in it, and it says, slide 2, do you want to go back where you left off? Because there's only 2 sheets there. Yes. Okay. Actually, I will go back where I left off. Welcome back. Picked up on slide 2. Got it. All right. So we'll go from current slide. And I'm recording all this nonsense. Okay. And let me get out of presenter view and into, what's that? If what? No, not yet. Yeah. When we finish chapter 2, which we're making decent progress in. Yeah, I think so. Yeah. All right. We are in section 2.3. In fact, I think, no. We did. See, I have a mark on the page. I don't know if this is from this time or last time. Had we started 2.3? Are we there or are we here?
Well, none of that looks familiar, so I'm going to stay there.
Okay. Yeah, I didn't remember doing this. I didn't see that mark on the page or I would have erased it.
Just wrapped up 2.3.
I think so. So we're starting 2.3 today. All right. Let's start with a definition here. And this is the part that I just go back and forth whether I ever even want to do anything in chapter 1 because it seems like they repeat most of it in chapter 2. So maybe I should have just started here.
I feel like it kind of
set the stage. Yeah. So maybe that's what I was thinking, but I just didn't want to leave any stone unturned or turn unstoned or whatever. Okay. The form of a linear first-order differential equation was given back in equation 7 in section 1.1, which hopefully we went over quickly. And here's the definition again, since neither of you have your books today, so let me write it down. First-order differential equation is any differential equation of this form. Let me get my pen activated. Oops. There. Okay. A, and they're calling it A sub 1 of x, dy, dy dx, plus A sub 0 of x, okay, times y is equal to some g of x. This is pretty close to the same type of presentation it had before. I think it's exactly the same. It's said to be linear in the variable y. Okay? Now, the derivative, and this is first order, okay? The derivative could have been second derivative, third derivative, fourth derivative. Doesn't matter how high that goes. It's just that none of the derivatives can be squared or cubed into the 1/2 power or something like that. And the y's can't be squared or cubed into the 1/2 power or something like that, or to the negative power. Those would not be linear. Okay. The g can be anything. It can be cubic, square root, sines, whatever. But these, the y's, and by the way, the a's can be that too. This could be a sine x. That's no problem. The x's don't have to be linear, but it's linear in the y. The y's and the derivatives of the y's have to all be first order. That's what the key is. Okay? So, And that also means that you can't have a y times a y prime. Even though they're first order, you can't have them in the same term multiplied by each other. Okay, that's said to be linear in the variable y. Now that's technically one way you can express it. Okay, quite often we don't write it that way. In fact, the standard form is a little different from that. In fact, what you do is, if you have it like this, here's what you do. Divide by a1 of x. Whoops. Okay. I hit the pen and it didn't come up. Okay, I think it did that time. Okay. Okay. Now, this goes away, so you have dy dx is equal to some other function, and they're calling this p of x times y equal some other function f of x. And you can name those functions anywhere you want to, anything you want to. This is a plus. Okay. Sorry about that. Okay. This is what they call the standard form. Yeah, you could write it the other way, but if you do, just go and divide by a1 of x and have it dy dx is some function of x. And remember, function of x can be anything. This almost guarantees it's a rational function if a of x is anything other than a constant. So that's fine. The x can be anything times y equal f. What's that?
As long as a1 of x
Wasn't zero, exactly. But if a1 of x was 0, you would have a linear function. You wouldn't have a differential equation, right? Okay, so that takes care of that, doesn't it? Okay, all right. So that's your standard form, okay? Now, we seek solutions for that on some interval for which both the coefficient functions p and f are continuous. So that then would tend to rule out when you have, if that was a rational function here and that was a rational function, then you have to exclude any vertical asymptotes you would have, or any places where those functions are defined. So therefore, this is only true where p and f are continuous. So that might limit the intervals over which these are true. Okay. But of course, if that was just a constant, or 1 or something, that wouldn't necessarily limit anything. Okay, before we examine the general procedure for solving equations of this form, we note that in some instances, that this form right here can be solved by separation of variables. So if you have it that you can, do it, okay? But a lot of times you can't, okay? Separation of variables generally is your first line of attack, okay? If you can do it, do it. Don't fiddle around with anything else. It's only if you can't, then. So let's just look at some that you might have, like dy dx plus 2xy is equal to 0, okay? That is a plus there. Ugly plus, but it's a plus, okay? Now that one, could you use separation of variables? Let's see. You could say dy dx, I can't write well, is equal to minus 2xy, then divide both sides by y, and yeah, that's separable, okay? Go that route, okay? How about this one? Dy dx is equal to y plus 5. What about that one? Yeah, that's separable. Write the derivative as a differential and divide by this, okay? So then you have dy over y plus 5 is equal to dx. Okay, I didn't do the other part. Let's do the dx over here and you. Yeah, I quit doing that. Wait. Huh?
You might want to put a key.
I did, but it didn't do it. Oh, there, it did something.
And now,
But you know what that's going to do? In the future, when I pull this up, it's going to be there, I think. But let's see.
what you can do is you can erase it at the end and then
Right.
key changes.
If it's erasable, that's the only problem. But I have to go through all this mess again. You don't see it, but I see it. It's presenter view. Okay. Okay. Question is, can I erase that? I don't know. We'll see. Okay, that is also differentiable. Okay. Separable. Okay. But this one, I can't. I don't know what it's doing. It's having a field day running in circles, I guess. It's chasing his tail. I don't know if I need to go completely out and come back. I don't know what it's doing. Any idea? You see what the problem is?
Yeah, I don't know.
I can't write anything as long as it's doing that. Let me do a Control-Alt-Delete. Sometimes that shakes it out of its doldrums. But I don't even know if that's going to come up. There we go. Okay.
Yeah, PowerPoint's
Not responding, not responding.
So you might as well end the tasks and then start over.
I don't have anything clicked. Restart the program, close the program, or wait for the program. This is so aggravating. I'm sure it's a PowerPoint problem. I don't think Screencast-O-Matic is involved with this part. Huh? Yeah, which is not at all unusual. This may take several minutes, okay? I wonder if I can cancel this one. Oh, now it says it's restarting. Okay.
That the document recovery.
Right.
You see where it says available files?
Do what?
Available files right there under
Yeah.
document recovery. Click on that above it. And
Available file. This one?
yeah.
Okay.
That's the one we have open.
Yeah.
You got it?
Okay, there we go.
And there you go.
So let's go from current slide. I think I'll lose all my writing.
That's
Yes,
probably
which is probably a good thing. Okay, let's get going again. How many times do I go through this? All right, we're here.
Say don't tempt it.
Okay,
Uh-oh, it shifted over.
I know. Okay, here's where we were without it. However, this, I need to get my pen back. Okay. All right. However, this really simple looking that one is not separable because
You can't
the x's
pull it.
and y's aren't multiplied, they're added or subtracted.
You can't put it in differential form like that.
No, to get it in differential form, you have to subtract
y from both sides, and then you have dy dx is equal to x minus y, and then dy is equal to x minus y dx, which is fine, but now it's not separate. You can't separate that y out. No way, Jose. Okay. So, what we're going to assume then from here on, for what we're going to be talking about here, is that you've already tried separation of variables. It hasn't worked, or you see it won't work, and then you proceed with this. Now, how do we go about solving these then? I can remember, I think I told you all the story before, that I was in calculus sequence when I was an undergraduate. My first 5 quarters of calculus, all the calculus I took, were under one professor, and he was fantastic. Hard as all get out, but he was an excellent teacher, laid it out for us, never let us catch up to where he was, but because we went through things so fast, we ended the 5th quarter with time to spare. We had about 2 weeks left. He said, that's all that we're going to do in calculus. Maybe it wasn't quite 2 weeks, but it was some time that we had at the end. He said, let me use the time rather than waste it just getting you ready for differential equations. So he did some of the easy and early things. He said, I remember this because I thought it was funny at the time, and now I'm more and more convinced it's true. He said, one of the big things about differential equations is they're all different, and you have all different. So what you do, you try tricks to see if you can get them to work. And the trick works, you call it a method. That just about nailed it down for the differential equation. So I'm going to show you a trick. And in the book, they call it a method because this trick happens to work. The method for solving, and we've all lost it now, but let's go back. And remember our form, which is dy dx plus p of x, y equal f of x. Quit doing this! This is so aggravating. Should I discard and see what happens? Okay, maybe this will be easier. Okay, oops.
It's already open.
Okay, so now I have to go through all this mess again. Hide presenter view. Okay. All right. Back where we started. This form, get my pen color again. dy dx plus p of x, y equal f of x. It doesn't matter. Yeah, this one, it didn't go as far. Okay, I don't know why it's doing this. Okay. Now, the method for solving this, if it's not separable, okay, hinges on a remarkable fact that the left-hand side of the equation can be recast into the form of an exact derivative of a product by multiplying both sides. Here's the trick. Multiplying both sides of the equation by a special function, mu of x. Okay. So we're going to multiply this side of the equation. This side of the equation, I don't know where to write it. I'll write it up here then. Mu of x. No. I swear. But keep didn't work as well as discard, did it?
But you'll keep the e.
Okay.
Click on the slide.
Oh, I see. Okay.
Yeah.
Last time it wouldn't let me do it. But I still got to do this again. I swear. Okay. Okay. I'm trying. Ah, there it goes. That time I had to do backwards. Okay. Now I've got to do this one.
At least this time it's not slid over.
Okay, but here's the other thing, though, and this is actually better. It's reduced like this, so this is not in the way, but now it's compressed like that. And maybe...
That's still easy to see.
Yeah, it reduces your size, but maybe now everything in here is writable, whereas before, when I was up here, it wasn't. Okay, and that may have been the problem. I don't know. Mu of x, okay? Yeah, multiply both sides by that. Mu of x. Okay. What does that give us? That gives us dy dx. I'm going to write the mu of x in front here. Plus p of x mu of x y equal f of x mu of x. Okay. Now, that doesn't look particularly pretty, does it? Okay? But here is a key. Okay. Now, all right. A little of an aside here.
Don't go too far to the side.
Okay, yeah. Here is something to observe. D by dx of this thing. Mu of x times y. Okay? We know how to do that. It's a product rule, right? That's equal to what?
U prime of x,
Okay, we'll write it that mu prime of x.
y,
Okay, y, why not?
plus
Plus
u of x.
u of x, y prime, right?
I was wondering if it was 1 or if it was just y, so yeah, y prime.
Okay, yeah, it's
Make
y
sure
prime.
it's just like a variable.
Yeah. Okay, yeah, because you see, you're taking it with respect to x, and derivative of mu with respect to x is mu prime times y, whatever that is. And then you're taking derivative of y with respect to x, which is what we're calling y prime. You could write it dy dx, okay, which is probably what we should, because that's what we have here. Okay, now, here is the deal, okay? What we have here, notice this term here, is this term right here, right?
Right.
Okay? Now,
And then if you take out the p of x, that's close to that.
right, it's,
Not quite the same.
yeah. If p of x, if mu prime is equal to p of x times mu of x. If that's the case, then we've got it, right? That's what this side is. So, that's the key. You just hit it. If p of x mu of x is equal to mu prime of x, then this is your product rule, okay? Right? That would be the left-hand side.
So the
Now.
dx with
Yeah. Now let's do this now. Let's write this as d mu dx is equal to P of x mu of x. Right? Okay. Now, this is separable by variables. Okay? That would be d mu over mu is equal to P of x dx. Right? Okay? And I can even do this. Okay? This right here would give log of mu, wouldn't it? Log of mu is equal to the integral of P of x dx. Okay? Which means that mu of x is equal to, this was scary. I just saw the little thing come up. If I'd have hit the screen just an instant sooner, it would have canceled out. I don't know why, but I just saw that do it. I thought, I'm so glad I didn't hit it. It's equal to e to the integral P of x dx. So that's the mu, that special function. That's the trick we're going to do, is multiply.
Plug that in to there.
Yeah. Okay. So we found out what that special mu is. It depends on what the p is. Okay. And it has to be integrable. But remember, we said that P of x has to be continuous. Remember, we said that on the integral where P of x has to be continuous.
So it would be.
Yeah. Yeah. Well, we hope. At least you can do it some way. You know, you can do it by numerical integration, if nothing else. Okay, but it is integrable in some way, and then that is it's a function of x. So yeah, you go from there. All right, that's the key. Okay. And technically, I should have written absolute value bars around the mu, because it has the, you can't take the log of something that's negative. Okay. Now, and one other thing I didn't do, we need a plus c in here. Okay, because that was an indefinite integral, so you have to have a plus c from taking this integral. Yeah. Yeah. And so I put the plus c over there, but you could have had it here.
Would you carry that over to the integral?
Okay, yeah, and that's the, no, you don't have to. You can do the integral of P of x dx, okay, but,
See, my thinking is it would
okay,
be CE.
yeah, exactly, that's what you get is your mu of x then becomes a c times this. That's where your constant comes in. It's not the same c as before, it's a different c. I should have just left it out. It's still a constant, okay. And even though there's an infinite number of choices of mu of x, constant multiples of this thing, they all produce the same desired result. Hence, we can simplify and choose that c to be 1. Okay, so we ran all the way around the circle there and said we can ignore it. Okay, just take it to be 1. Well, it's, any of them would work. Any of them would work, so why not choose easy? Okay, that's basically what we're doing. We made it up to begin with, so we can choose which one we want. We want the one with c is equal to 1. That's the one we're going to use. Okay, so that's what we're going to do here. Okay, that's now called the integrating factor that we'll use in our original equation. Okay, so let's go back to what we had then.
Yeah, my question here is, so when we run into something like this, will we be using that, or will we have to go through this process to find the integrating?
Okay, well notice that, sort of to answer your question, but we're going to skip something later. Basically, all you do when you have that as an equation, forget about p of x, okay? Just integrate, first thing you do, integrate your p of x dx. It's a constant, it's a continuous function,
integrate it if you can, okay? Usually you can. Whatever that comes out to, that's the function you're going to e to the that, okay? And then that's what you multiply by both sides of the equation. But do you actually have to do that? Let's wait and see. Okay. So let's go back and retrace what we've done so far. Now, remember, this came directly from that, right? But this we noticed was with that value in there, that was exactly this thing, d by dx of that. So this side of the equation is d by dx of mu of x y is equal to, okay, I didn't see that, but maybe it happened, I don't know. You saw the little star rather than a dot. And that's what happens. If I hit while it's still that, I don't know why, but that's what does it, I think. Okay. Okay. So this side is equal to f of x, mu of x. Okay. That's what we've got so far. Okay. But rather than, I'm going to have to erase some. It's just too crowded. Okay. You want to? Okay, you wouldn't be lost if I did that. Okay. Hey, I erased it all in that state. That's scary. Okay. I think this was what I said. It didn't erase it. And I think when I saved it, that saved it, and now it's part of the slide forever. I've just got to do a new one. Okay. Okay. All right. So what we have now, there's a real big part of me that wants to, instead, okay. I'm going to rewrite this. The mu of x is equal to e to the integral of p of x dx. So I'm not going to write mu of x anymore. I'm going to write that. It's messy. It takes too much time to write, but that's what we got. So that was going to be e to the integral of p of x dx, okay, times dy dx, okay, plus, and this is the part that we already did that, so let me just cut to the next step, sorry. What this came out being was, remember this p of x times y, that was what? We already had that one on, so I'm going to, let me just erase that part. Get back down to, because I'm going to need the room later, I think. Okay. So, I think this is where I left off. D by dx of, this is my mu, e to the integral p of x dx, okay, times y. Written mu so much now I can't write a y. Okay. Y, okay. Okay. This is equal to, and remember, this was this side, and this side was our mu of x. Remember, we multiply this by mu of x too. But that mu of x was this, so it's e to the integral p of x dx times f of x. That's a product. Okay. Now,
Why do we call this the integrating factor? That's sort of the question here. If you integrate both sides of this equation, in other words, I kind of hate to say this, but write this in differential form. So this is d of that the dx comes over here. That's in differential form. If you integrate this, integrate both sides of this equation, integrate this, then this obviously becomes e to the integral of p of x dx times y, because that's just the differential. You integrate the differential, you get what's left, okay? And if you integrate this, which has got an integral of an integral, okay, again, you introduce the c here, but you, because when you integrate that, you get a c. I'm going to put the c over here with this, and this is now the integral of e to the integral of p of x dx, okay, f of x dx plus c, okay. Now, what we're going to do now is divide both sides of the equation by this, e to the integral p of x dx. This is divided by e to the integral p of x dx. Okay. It almost feels like we're running around in circles, okay? But now we've got what the y is, okay? So let me write that a little clearer. I just got to find the place to write it, okay? I don't think it's going to let me erase that, but I can't erase this. Now I regret that I tried to erase it. Okay. And this thing, I hit the pen and nothing happens. There we go. Okay. That star comes out again and nothing happens. I hate that star. Okay. Okay. Now, what does this give us? Y is equal to, this is your solution, by the way, if you hadn't noticed yet. Now, they write this as e to the minus the integral. Yuck. E to the minus integral of p of x dx, okay, because it was e to that in the denominator. We're moving it up so it becomes that, times the integral of e to the integral of p of x dx, f of x dx, plus c times e to the minus integral of p of x dx. Okay. Goodness gracious. Okay. Now, don't worry about trying to remember that formula. Okay. Here's what you remember. Okay.
So where did the second e to the negative p or integral?
Okay.
I see where the first one came from because you brought it up from the bottom.
Yeah, but you see this is also that too.
Oh.
These are separate terms. So put it with this, put it with that. Which almost begs the difference. Why don't you just factor it out front, you know, and have a plus c, you know, but I'm writing it the way the book did, and I'm sure there must be a reason for it, so we're going to get there.
Because it's like e to the integral p, that's under 1 as well, out in front of the integral.
Okay, what?
You have, that's under the integral, and then also...
Yeah, it's under here and it's under there.
Okay,
Yeah, right,
plus
right.
c.
Yeah, the c is a separate term.
C is separate.
Yeah, okay.
That's
Yeah, that's what it was. Okay, now, Now, here are the steps, if you didn't remember them. If you had an a of x or something like that in front of that dy dx, get it in this form. Get it in this form. P of x, dy dx equal p of xy plus f of x. Plus p of xy equal f of x. Be sure you're in that form to begin with. From the standard form of the equation, then identify what that p of x is. Okay? If you had divided by an a of x here, this has been an a0 of x, whatever that thing turns out to be, that's your p of x. Okay? So you have the negative derivative here of whatever your function of x is in front of the y, that's your p of x. Okay? So whatever that is, okay, then find that integrating factor. Okay? And don't worry about a constant at this point. Okay? So figure out what the integral of this is. And that's going to be a function of x. Don't introduce a constant. Just find out what it is. And then do e to that function. That's going to be your thing. So you don't carry around integral of p to x. Go and calculate it, whatever that is. Identify it first. Calculate it second. Okay? Now, multiply both sides of the standard form of the equation by the integrating factor. Okay? E to the whatever. Okay, that's your integrating factor. Okay. The left-hand side of the resulting equation is automatically the derivative of product of the integrating factor times y. And so then integrate both sides and solve for y. And that's what it is. It's a lot easier to do in person than it is otherwise. Now, and how we're going to start, and let's see. Can I try this? Can I try to white the screen?
You could, yeah.
Let's try that. Ha! It did, didn't it?
Yeah.
Okay.
You won't be able to erase all of them.
Yeah, I won't be able to erase on this anymore. I'll unwhite it and white it. Okay. So here's, I love this. dy dx minus 3y is equal to 0. Okay. Now what you notice about it first?
I like this form.
I know, it's a lot simpler, isn't it? Now, what I want you to do first, how would you solve this if it
Put it in different form, right?
okay. Okay. What I would do, I would separate variables. I would. So I'm going to do that now, and we're going to see what the answer is. Then we're going to do it the other way and see if we get the same answer. Yeah, add 3y to both sides. That gives you dy dx is equal to 3y. So that's dy over 3y is equal to dx. By that? Everybody follow? Okay. Integrate, and you get the log of 3y, I guess I should put it in here, is equal to x plus c. So, well, I may want to modify that. I'll call it C1 for now. Okay, take an exponential of both sides, and that gives you 3y is equal to e to the x times e to the c1, which I'm going to call c. So y is equal to, I really want to say c divided by 3 is also a constant. So call that c, some c e to the x. Let's see if that works. Or maybe I do need a 3 in there, don't I? dy dx would be,
You're multiplying by 1/3.
yeah. Well, let me see. If I take a derivative of that, I get y prime would be c e to the x.
No, we're not going back.
I just swear. I love PowerPoint. It's just such a wonderful package. It's a Microsoft, isn't it? Okay. I guess I
would just erase all ink. That way you don't have to worry about losing
Okay.
everything.
Well, I got to get this off of there then. What aggravates me, though, that's an incomplete thing. I want to go on the right end to make it correct. It's not correct without this in there. But who cares? We're not paying any attention to it anyway, but it just bugs me. Okay, ignore that. Okay, so what we had down to was y is equal to ce to the x. Y prime was equal to ce to the x. And we had y prime, what was our thing? Minus 3y is equal to 0. So that would be ce to the x minus, yeah, I do need that third in there, I think. Yeah, I've got to have that in there. So 1/3 e to the, yeah. Yeah. No, okay. Let me slow down a minute here. I'm going in circles. Yeah. Okay. Let's start over. Well, let me. All right. Okay. The pen came back that time. Okay. Let's start back over. We had dy over 3y equal dx. Okay. So this was log 3y equal x, and we'll forget about the c for now. That'd be e. If I did a e, that would be 3y is equal to e to the x with a constant. We'll go to that ce to the x, and y is equal to, ce to the x over 3. Okay. And then y prime would be ce to the x over 3, and our original thing was y prime dy dx minus 3y equals, no, yeah.
When you have to do a quotient rule, when you take a derivative, how do you low? Or would that even matter?
Okay.
It's just a 3.
Why is this causing me such headaches? E to the that would be e to the that, okay? And that would be 3y is equal to okay. So y would be c, okay. Y prime would be c over 3 times e to the x. I mean that, but then this doesn't work, does it? That would be c e to the x over 3 minus 3 times c e to the x over 3. That doesn't equal 0. our answer really should be, it should be exactly what I said here originally. Y is equal to C e to the x. Okay? That's what I think it should be. But then, that doesn't fit the original equation. dy dx is equal to C e to the x. Okay? Then you had C e to the x minus 3 C e to the x equals 0, and it doesn't. Unless, of course, huh?
The second one should be over 3. That's the only thing that
Yeah, I know, but if you put it over 3, then the other one's over 3, and it really isn't.
book doesn't offer much for this, does it?
Oh, wait. Here's how they get around it. Okay, multiply both sides of the equation by 3 there. Okay, if you do that, now you got log y is equal to 3x, right? Now we get log y is equal to C e to the 3x. Okay, that's your answer.
And then it's
Now it works. Okay. Divide by 3. Don't carry the 3 with it. That's where I made a mistake. So that's your answer. So let me erase all the rest of this garbage. Sorry about that. This. Ha!
So y is equal to C e to 3x, and then y prime would be C e to 3x over 3.
Y prime times 3. Right? See, this part is out of there. This part is out of there. All this is out of there. Okay. Sorry about that. Okay. Now the pen's here. I think hopefully it'll stay here. Then y prime is equal to 3c e to the 3x. Right? Chain rule. Okay. And then when you put that in, you get 3c e to the 3x minus 3c e to the 3x. Sure enough, that's equal to 0. So yeah, that works. Okay.
So much for
Got
a
it.
simple problem.
Yeah. No, that was the easy way to do it. Here's the harder way. Okay. Here's our problem. Remember our problem? dy dx minus 3y is equal to 0. Okay.
This might actually look simpler now.
Now it might. Yeah. Okay. Now, what is your p of x? P of x is equal to negative 3. Right? Because that was our form. For some reason, they had the plus in there, so that's our form. So what do we do first? We integrate that negative 3 dx. Okay? So that's going to be negative 3x. Okay? Once we've done that, we raise e to the minus 3x. That's our integrating factor. We multiply that by both sides of the equation. So e to the minus 3x dy dx minus 3y. Oh, I'm sorry, I didn't multiply that.
Negative 3.
Yeah, let me.
Well,
Yeah, I can put it here. E to the minus 3x equals 0, because that times 0 is still 0. And that thing obviously isn't 0. Okay. Now, what this side of the equation is d of e to the minus 3x have another 3 in there. That's a, no, yeah, that's it right there. Right? Okay. Isn't this thing here, this? Because if you take the derivative of this, you get e to the minus 3x dy plus derivative of this, which is a minus 3e to the minus 3x times y. Yeah. So that's what that is. Okay. And this is d, and then do our dx over here. So this gives you e to the minus 3x. Oh, I'm sorry. I was repeating something I don't need to repeat, especially since I don't have enough room to repeat it. Okay. Well, I think I do need to write it. E to the minus 3x y is equal to 0. So y is equal to e to the minus, it's e to the 3x. Okay. Now, I forgot my c's in there somewhere. Oh yeah, right here, when I integrated that, that gave me a c. And I could, this one right here would have been a c, and then a c1, and then.
Okay, so, alright, walk me through the part where you took it from the equation to the d of e to the negative 3xy. How did you get to there?
What? From here to here or here to there?
The first one.
Here to here. Okay, I noted that this thing here is, by product rule, the derivative of this product. Okay, because when you take the derivative of this, let's go this way. When you take the derivative of this, it's the first times the derivative of the second, plus the second times the derivative of the first.
So you just have to take the antiderivative to get you there?
Okay, then I integrate both sides. Write it in differential form, integrate. That just gives me this is equal to actually c. That should be a c there. Okay, c1, and then I multiply. Or actually, it's a c.
So you kind of worked it backwards.
Kinda. I mean, yeah, it's a trick. Okay. Okay. This was a c, and then see, what you're trying to do is lose the derivative of y. You want what y is. That's what you're looking for. What's y? Okay? And since you can get this thing to be a product, that's why you call it integrating factor. You get this to be a product rule of a derivative with just a y in it. Then when you integrate both sides of this, you have a y with something else, then you multiply by that something else, or divide by that something else, or whatever, and that gives you a y by itself. And sure enough, we did get the same thing after much thing. So you don't need to memorize a formula with all those integrals and e's and stuff. Just do the steps and let them take care of themselves. Let's do one that we can't do by, okay, now, are we out of time?
No, we got 15 minutes. I just need to do another one of these.
Okay, you want to do another one? Look at that one while longer.
Do another one.
Okay, let's do another one. Okay, now,
Not really grasping the whole thing.
okay,
Maybe after I do another one.
do we want to go to a white screen or erase everything on this
Just erase everything.
one? Okay, you like seeing that mess at the top, don't you? Okay,
You just scribble through it.
okay, that might be easier. Okay, all right, here's the next one. Solve this one. dy dx minus 3y is equal to 6. Okay. Now, frankly, this one I think we can also do by separation of variables. And this time we'll try to do it a little more carefully. Okay. So add 3y to both sides and you get dy dx is equal to 3y plus 6. By that? Okay. Now do a dy over, I'm going to cheat a little bit and make it a y plus 2 is equal to 3 dx. See what I did? I don't know if I need to, but I just don't like carrying around extra garbage that I don't need. So I factored out the 3 there and divided by y plus 2 and got the 3 over there. I don't know if that's helpful or not. I hope it will be. This then becomes, if you integrate both sides here, you get the log, natural log of y plus 2 is equal to 3x. And you could do a plus c if you wanted to. When you take the e of both sides, you get y plus 2 is equal to let's call it ce to the 3x. And then subtract 2. Y is equal to 2 minus, no. Minus 2, yeah. Okay.
See, that's easy. The other
Right.
way.
Is ce to the 3x minus 2. Just remember the minus 2 is separate.
So that's what we check against.
Okay. Well, I want to check it first and make sure that works. So your dy dx is equal to 3ce to the 3x, right? Yeah, okay. So then this would be 3ce to the 3x minus 3 times ce to the 3 times ce to the 3x minus 2 equals 6.
You multiply that negative 3 out, those two cancel out.
Right.
You're left with,
Yeah. And this one, that goes out. This makes 6 equals 6. Yeah. Yeah. So, yeah, that works. We know it works. All right. So, that was just checking. So, let me get rid of my checking, because I might need all the room I can get. Now let's just leave the answer. Are you okay with just the answer?
just the answer.
Okay. And that minus 2 was part of the answer. Okay. I don't want to erase that. Okay. Now, let's do it our other way. Now, what's that? This is the standard form.
So we gotta find P of X.
So P of X is what? Negative 3. We're used to that, aren't we? So the integral of P of X dx is equal to the integral of negative 3 dx, which is minus 3x, right? Okay. Then we take e to that, e to the minus 3x. That's our integrating factor. Multiply it by both sides of this, and you get e to the minus 3x dy dx. Okay, let's see. Do I want to do this? Do I want to?
I just did negative 3y, e to the negative 3x.
Yeah, okay. That's why I was trying to decide whether I wanted to do it in parentheses or not. I guess we'll do it that way. Minus 3y e to the minus 3x is equal to e to the
Well, 6 to the negative 3x.
6e to the minus 3x. Okay.
Now we've got to find
Okay. And you notice that this is d by dx of
so we need to basically kind of look and see what derivative made that, or
what's that?
what that's the derivative of.
Yeah.
So that'd be a quotient rule, right? It's subtraction.
No. The subtraction comes from the chain rule there. Yeah. So it's always going to be a product rule. And that's going to be e to the minus 3x times y. That's exactly what it's going to be, okay? In fact, it's going to be that every time, I think. I want to hold that. Let's just see if that's true. Derivative of this would be this times derivative of that. We got it. And derivative of plus this times derivative of that. Derivative of this is minus 3 e to the minus 3x. So yeah, minus 3 e to, yeah. So that is right. And that's equal to 6e to the minus 3x. Okay? Take our dx from here and move it over there. I'm not missing words anymore. Okay? I'm going to do it. Okay? Write it as a differential. All right. So this gives me e to the minus 3xy when you take the derivative of that. And this is, that's when you integrate that. And when you integrate this, you get minus 2 e to the minus 3x. And you need to have a plus c somewhere here.
Throw it in between the two of these.
Huh? Yeah, let's put it right there. Okay?
I like to keep it anyway.
Right. And then divide by, or multiply by e to the 3x.
Divide by
Wait a minute.
-3x.
No, I think you, let's see. No, you can't do what we just said. Okay. I was trying to skip too many steps and we can't. Let's back up and do that a little more slowly. Okay. When you take this integral here, okay, you've taken that one's correct. Okay. When you take this one, that gives you your 2, such a pain. -2, yeah, what I had before. Okay, let's, okay. It's a minus 2 e to the minus 3x plus c. You need that plus c in there, I think, okay? Because now, what we're going to do, is multiply both sides of the equation by e to the minus 3x. E to the 3x. Okay? And sure enough, this one wipes that out, this one wipes that out. Okay? And that gives you, right, the way we've got it here, minus 2 plus c e to the 3x. And that's the same thing we got here, only in the first one. So that's what your y is equal to. And sure enough, that's it. What you have to remember is when these are indefinite intervals, you've got to have that plus c. You can't start swapping them around anymore because you're not taking e to the thing anymore. Yeah. So you have to read that word loss.
And then that is?
And that's the same answer as we had before. Let's see if they got it. Y is equal to -2 plus c e to the 3x. And they say that's good for all x's from negative infinity to positive infinity. And there's a part of me that has a little bit of hesitation there. But I guess none. You see, there's a part of me that says, but wait, when you do the separation of variables, you have to do log of absolute values, but then you're not sure which ones will make that negative. But in reality, none of them do. No x value you put in here is going to make this y. Whoa. Can I say that? No.
Well, it's going to be some constant times.
Yeah. Oh, remember that was log of x plus 2. So yeah, this thing, y plus 2. So sure enough, this thing is always positive. Okay. As
long as C is positive, I think.
Okay, we're not going to worry about the C now. Okay,
So
that's good for all x's, they say. Okay. Now,
we have like 2 minutes.
2 minutes. I was going to try to see, y'all don't have your books, and I sure can't draw this graph in 2 minutes, okay? I don't, yeah. Can y'all see that?
Yeah.
These are your various curves. This solution here, minus 2 plus CE to the 3x for different values. Here's your y is equal minus 2. For different C's, you either get going up here or you get coming down here, depending on whether C is positive or negative, you know, and whatever. So that does seem like it's good for every real number x. It's just, you know, it's a positive exponential that way, a negative exponential that way, but they're around the line y is equal to -2. All right. Now, is there time for any talk about the general solution? Suppose again that functions p and f are continuous on a common interval I. In the steps leading to 4, they refer to these, okay, to that integrating factor multiplied in there. We showed that if 2 has a solution on I, then it must be of the form given, okay, conversely, okay. Boy, they just have so many words here. And then they say, in other words, okay.
You didn't have enough already?
Yeah. They call this form here the one that had all the integrating factor in it. The one they said don't memorize, okay? All those e to the minus, you know, of the integral, the px, and stuff like that. The general solution of the differential equation. Now, by writing that in normal form, okay. Hey, no, this gets into partials. I don't think we want to go there. I cannot see that is clarifying anything. So we'll begin next time with example 3. I mean, they just sort of went around and around, but I couldn't wind up seeing that they came up with anything at the end. So there's example 3. Homework exercises here. Do any of the odds 1 through 23. And they do have the, well, let's see. Let's look in the back. This is 2, 3. Let's see which ones of those they have in the back. 2, 3.
Oh, yeah,
This is the book that doesn't have everything. 1 through 23, it looks like they have all those. Okay. Okay. Stop there at 23 because we're going to do the rest of them after we do example 3. All right. Good deal. When we finish chapter 2, and we're in 2.3 now, and we still have to do 2.4 and 2.5, and I'll debate whether I'm going to do 2.6. I guess I'll do 2.6 also. That's it. So when we finish 2.6, I'll give you a test. Okay. So we are more than halfway through to the test. We'll see. All right. Good deal. What's that? No. Cal 2 got one yesterday, but Cal 3 did not.